Starting recording, I assume now. Hopefully it's recording. It's saying it's recording. Well, welcome to the Python Meetup, monthly Python Meetup. We're still doing this as online meetups. Hopefully we'll be able to do it soon without in-person meetup, hopefully very soon. We all want to actually go back to the time of the nice meetups that we used to have. However, in the meantime, during COVID times, we actually have two talks that are very interesting. The first one will be by Rencheng, who is going to show you a library called Folium and show you how he used it to show how COVID is spread in Austin. You will see it. Later on, we'll have Erik Case, and he will be showing you a different library and hyperopt that will show you that is related to machine learning and how to optimize hyperparameters. So Rencheng, please, you'll go first.
Yeah.
And I will mute myself and let you take over the screen. If you can share your screen, go ahead, please.
Sure, thank you. Can you see my screen?
Yes.
Okay, nice. Yeah, hi everyone. Thanks for the invitation. I'm very happy to present a project I did recently using Python. So today my presentation is how to make interactive maps with Python using a library called Folium. My name is Rencheng. First, a little bit about myself. Currently, I'm a PhD student at UT Austin. My major is petroleum engineering, but my research is very heavy on computational engineering. My research is on numerical modeling of subsurface reactive flow processes. So normally, I will write some C++ code to solve a system of PDE equations. That's my routine work for my research. On the side, also like sports, but currently due to the COVID-19, I couldn't do much. And also, I'm interested in doing some small projects on the side. That's it for today's presentation. That's the outline. First, I will introduce some background and motivation for making maps. Then I will go through an example to show how we can use Python to make some pretty maps. So first, why do we make maps? I think maps are useful. My background is petroleum engineering. We deal with lots of spatial data analysis. For example, I took a course called geostatistics. Basically, we study how to model or interpret data in the subsurface, since we only have very few data we obtain from drilling wells. So in between wells, we need to use some statistics to model the data to make a smooth distribution of the parameters we want to know. So here I'm showing a kind of a more common example how we use the map. I'm showing Starbucks a map from Starbucks website. It's an interactive map. Basically, if we want to find a Starbucks store, we put a zip code or maybe city name on the search box. Then we will find the Starbucks nearby. We can see those green dots represent different locations. And if we click on one location, a special marker will show up and tell us this the one you are looking at. I think the map is very convenient for our daily life. Sorry, is there a question?
Okay, go on. If there'll be a question, then I'll ask. Sometimes people don't mute themselves. You're fine.
Yeah. So next, I want to introduce different types of maps from my understanding. So one type of map is called base map. So I'm showing the different base maps for Texas state. One is a street map of Texas. It shows the major roads and streets. On the right is showing a kind of a satellite imagery map. So the base map provides the background settings for some customized map. And those maps are usually available from some big projects or big companies. For example, OpenStreetMap is an open source project. So they develop those base maps. And some big companies like Google, we have Google Map, and the Bing from Microsoft. ESRI is a commercial company for the GIS industry. I will discuss a little bit later on what is GIS. And another type of map is called a thematic map. Usually we deal with this kind of map in our life. That's also the focus of this talk today. Still, I'm using the Starbucks map as an example. So this kind of thematic map is showing a particular theme or particular information of interest. For example, right now we are interested in the information of Starbucks store locations. We can say at the back for the background is the street map as the base map, and on top of that we have markers which shows the store locations. So those markers make this map as a thematic map. So this is useful when we want to visualize or extract some information. And also I think it's also useful for some spatial data analysis. For example, we can first visualize some spatial data on a map. It's easier for us to figure out some spatial trends from the map instead of looking at in a tabular data fashion. So actually making maps is a one task of GIS. So GIS represents Geographic Information System. So the definition for GIS is a computer system for capturing, storing, checking, and displaying data related to spatial positions on the Earth. So for our discussion today, I'm just focused on how to make maps with Python rather than talking about the GIS. That's a big discipline. So we can say this is a illustration of GIS. They collect different sources of data and visualize on the map using different layers. So making map is one step of the GIS work. So in Python, we have several mapping libraries. We can use those to make maps in Python. So first, I think everyone is very familiar with this library, matplot library. So we can plot different data on the map using matplot. But for this one, the limitation is I call it solo maps. That means if someone don't know Python or programming, it's very difficult for them to use the map you developed using Python. Another option is a Folium library. So later on in this talk, I will go through a demonstration example for this library. So basically, this library makes a web-based interactive maps. The philosophy of this library is we can manipulate the data in Python, then visualize it in a leaflet map via Folium. So a leaflet is a very powerful open source JavaScript library for making interactive maps. So that means even though Folium is a Python library, but the engine for making maps is the leaflet under the hood. So Folium is like glue to bind the Python and leaflet together. And besides the Folium library, we also have some supporting libraries to deal with the data or other features in the map. One is called GeoPandas. So from the name, we can see it's an extension of the Pandas library. The specialty is it provides geospatial operations in Pandas. So this GeoPandas library depends on another library called Shipley. So Shipley library handles the geometric objects like polygons or something else. Another small library called Branca. So Branca is a kind of a byproduct of the Folium library. When they develop Folium, they also develop Branca, and later on they separate Branca as a kind of individual library to support the Folium. So Branca deal with some features which is not specifically for maps. For example, we can use Branca to create a color map. So that's the overview of the mapping libraries in Python. Next, I will go through an example to show how it works in Python using Folium. So here, the example is to map COVID-19 cases in Austin area. The reason I did this project is so initially, I think in March, when we start to have the outbreak of the COVID-19 in Austin, Austin government starts a website. So it has a map to show the spatial distribution of the COVID-19 cases. So here on this slide, the figure is a map screenshot from a government website on, and it's in March, at the end of March. So I find this map is not very easy to use. So firstly, if we look at the base map, it doesn't have major road streets or landmarks for us to figure out where we are. So we are mostly familiar with some major roads like I-35 or MOPAC, but we cannot see those streets on the base map. So it's very difficult to locate our own positions or the places of interest. But I think right now the website has been improved on the government's website. It provides a better street map as a base map, but still the opacity of those zip regions is not very easy to see through the base map. Another difficulty is we cannot search for the places of interest. So what we have to kind of use a try and error method. If we want to find a region of interest, we kind of know where is that, maybe on that corner, maybe on the left or on the right corner, and then we click several regions. If it's showing the zip code what we are looking for, then that's it. But it takes some time to click at least the several regions until we find it. Then for this project, my objective is to improve this map and help people track the number of cases more easily in an interactive way. And next, I will talk about the workflow for making maps. So before we make maps, we need to gather some data. One data is kind of geometry information of the zip code regions. I find this information from this website. So those information is stored in a JSON file. It's basically a special JSON file. So we can see on the left is showing the original data. The specialty is they have geometry information here. The zip code region is basically a polygon shape. It has multiple coordinates to define the shape of the polygon. It's basically multiple tuples of longitude and latitude information. If we plot the GeoJSON file on a map, those purple region is the visualization of the GeoJSON file. So that's one type of data we need. Next, another data is the COVID-19 cases data. The data source is from the Austin government website, but it doesn't provide the tabular data. It only provides the map. When we click on the polygon block, it will show a box. In the box, it has a zip code information and a count number. So the manual way is to click all the blocks and get the count number with respect to the zip code information. So here I use a software called PassHub to automatically acquire data from this website. So here on the left is showing the commands to do the scraping work. In the middle is the website. And at the bottom, that's the output. That's the result of the data we want. Basically, it shows the zip code and count information. That's written in a JSON file. So that's the two type of data we need to map the COVID-19 cases in Austin by a zip code. So next part is to do the mapping in Python. So here I'm putting the screenshots of the code snippets in the slides. So first, we load the libraries we need for this project. As I introduced before, Folium and Branca libraries are for mapping purpose. And GeoPandas, Pandas, JSON are for dealing with loading data and manipulating data. So the first step is to load the GeoJSON file of Austin zip code regions. There's a function called read file from GeoPandas library. We tell the function the file name and the driver basically means the format of this file is the GeoJSON format. After that, that's the output. That's the tabular fashion of this GeoJSON data. So we can see that the specialty of the GeoJSON is the geometry column and shape area and shape length column. The geometry basically contains lots of longitude and latitude information for the contour of the polygons. the second data is the count data by zip code. It's in a JSON file we get from web scraping. So we use JSON library in Python to load the data first. And then we just take the zip region. It's kind of a data structure. We just take this part, put it in the count data. That's the visualization of count data. Basically, it has two columns, zip code and count. So right now it's still in the JSON format. Later on, we use pandas library to convert this JSON data to Python data frame. So this line of code converts the data type of zip code column from a number type to the string type. So the purpose for this one is later on we need to merge these two sources of data. So we want the zip code as our key. So the key must, I think the key needs to be in the string type. So after loading the data, there are small issue for the count information. When I scrape the data, there are some duplicate information. The thing is, if you click on one polygon, sometimes it will show the information of several polygons nearby. So that causes some redundancy in our data. To reduce this redundancy, I use another function called drop duplicates in pandas library to drop all those duplicate data and just keep one in our data frame. After we load the proper data, the next step is to put the data in a single place. So here we have a GeoPandas data frame which describe the zip code polygon geometry information. Another data is the count information. What I did here is to merge these two data together. So the count information will be merged into the geometry, the polygon geometry information. Right, the zip code is the merge key, and the count is the added data. So right now we have our data ready. So we are about to create the map. Before that, so this slide just to show some cosmetic work. We define a color scale depending on the minimum and maximum count. So this color map shows. So in the red, if it's hot, that means the number is high. The second part is to define a style function for the polygons. Basically, when we map those information, we will put a polygon on top of a base map. We need to define the line weight and line color of the kind of contour of the polygon geometry, and also we need the fill color and fill opacity for those polygons. Since we don't have, I mean, in some zip code regions, the data is not available, or there's no cases. We need to do some special treatment for those. Basically, we have a light gray color in those regions without data, and opacity there for the opacity. Those polygons are transparent if we don't have data in that area. And for the regions with with the data, we allow a little bit transparency, so we can see through the polygons. Since we want to look at some landmarks or streets on the base map. After cosmetic work, we start make our maps. The first step is to initialize the base map. So this line of code starts the the map. The arguments, the first argument allocation defines the center of the base map. So here I set is latitude and longitude of Austin. Then the map will be open as the with Austin as the center. And zoom start means the initial zooming level of our map. So that's the current map we get after this code. Next, we need to add another layer on the base map. The layer, I call it zip code layer. That's the code to do this work. There's a function called GeoJSON in Folium library. Basically, this function adds a GeoJSON layer on the base map. Austin, so if we look at the arguments, Austin is basically our data frame to hold all the data we need. The name argument is the name of this layer. So later on, we will use that in our layer control switch. Style function. So we defined in the previous slide. It basically regulates how we want to fill those polygon block. There are some extra features that I added. One is called highlight. That means if we look at this example, if I put my mouse on, if I hover my mouse on that polygon, the line weight increases. So we have a thicker line to highlight that polygon. Another feature is called tooltip. Basically, if we hover the mouse over that polygon, a box with some information will pop up. So here I chose to show the zip code information and the corresponding count information. So this is the map after we use this function. Next up is to add a search feature. There are several plugins in this library. So the search, here I use the search plugin. Still, if we look at the argument layer, that means on which layer we will search for information. Right now we have only one layer, the zip code layer. The geo type is to tell the function what kind of geometry in your layer. So here we have the polygon type. So sometimes maybe it's a point, maybe it's a line. The placeholder basically, before we search anything, we can put some kind of helper information in this search box. It will show search for zip code. So that tells people what kind of information is expected. Clasp basically means, so here we set it as a false. So this search box is not clasped forever. If we set as true, if we don't use this search box, it will become a smaller button in this corner. If we click that button, it will pop up a search box. The search label is the zip code. That's the key to look up the information. So after this one, we have the search box. We type in certain zip code. For example, here is 78701. The map will find this polygon, and it will zoom to that polygon. And if we put the mouse on that polygon, it will show up the tooltip information. At the end, we add a layer control switch. Basically, even though we add a layer in our map, but we want to have a switch. By adding this switch, we can remove the layer from the map. So later on, I can show the website to show how this switch works. So the final map is published in this link. And here I'm showing the screenshots of the map on computer on the left, and on the right is the map on the cell phone. I think that's the end of my presentation. Maybe before the question section, I just show on the website. So here's the website. We publish the map. So if I refresh, so that's the map, the original map, and I didn't introduce the legend part in the presentation, so we can add the legend to show some information and explain what this map is showing. So here's the search box. If we type 78702, so it will zoom to this region showing the count information. We can zoom in, and the color map is showing on the right top corner. So it's scaling to the real-time data. And this is the layer control switch. So OpenStreetMap is that's the base map. That's always on our website. But we can choose to close the zip code layer by clicking the switch. So here, right now we don't have that layer showing up. If we want to make it back, we just click. Right now we have that back. And this base map is provided by the OpenStreetMap project I mentioned before. I think that's it, and that's all what I want to show.
Well, thank you, Rencheng.
Yeah.
Thank you very much. I suggest that anyone who's interested, unmute yourself, will clap, and then ask some questions. So please unmute yourself and clap. We'll make some noise and then we'll mute everyone again. So thank you.
Thank you.
No problem.
And now, a few questions. It's kind of hard to do this clapping thing, but it sometimes works. I've seen it work nicely. So I will start with one question, and anyone who has a question, please unmute yourself and join in. But I'll start. Rencheng, when you publish the map eventually, how do you publish it? It's an HTML file, or do you have to create some web server? It creates it for you. How does it work?
I use a GitHub page as my server. So since right now it's a static web page, so I can use GitHub as long as it's not dynamic. Yeah.
No, it's dynamic enough. A lot of the graphic libraries are going towards the direction of putting interactivity inside. So if you look at Holoviz, then you will see it. But there are many examples of all sorts of visualization libraries that
Yes.
now produce static web pages that you can use. So Folium produces a static web page for you as well, embedded with all the information, correct?
Yes, yes. So it's interactive, but since it doesn't require any kind of data input, so it's still, I mean, static web page in terms of classification, but it's interactive.
And you update it daily, or how does it work? Like you just run it every day, or does it run by itself?
No, I cannot make it run itself. It's not fully automatic. So what I did is every day, maybe after dinner, so the government will update their data on their website. Then I will run the web scraping software to acquire data, and then I just click one button in the Jupyter notebook. It will update the map. Then I will use Gate to push the change. Then that's it.
Okay.
Yeah.
Any other questions? Well, apparently everyone is like not looking at the COVID map because they're afraid of it. I see,
Yeah,
Eric. Eric, you have a question?
No.
No. Okay, Rencheng.
Yeah.
If there are no more questions, if anyone has more questions, you can send them to the Meetup page later. And if I spot them, I'll send them to. I'll ask Rencheng to answer them. Rencheng, thank you very much.
Sure.
I'm
Yeah,
always
no problem.
amazed by the ingenuity of the people in Austin, and like I was really amazed when I saw when you sent me the map the first time. Really, thank you for doing this.
Yeah, I mean that's the power of the library. Yeah, I'm just applying that to make some specific maps. Yeah, the library is really powerful.
The libraries are one thing, but the people who do this are also, and many of them are in Austin. This is how we keep up this Austin Python meetup for quite a while. We have people like this. So,
Sure.
Rencheng, thank you very much again.
Thank you.
Rencheng, we're going to move into Erik. So if you can move the video away, and Erik can take the screen in a second.
Sure.
Here we go. Erik. Erik is going to talk about some machine learning support library. It's called hyperopt, and he will present it much better than me. So, Erik, go ahead and present. Tell us about hyperopt.
Will do. First of all, thanks for letting me speak. I think this will be a pretty brief, high-level overview. My name's Erik Case. I'm a senior data scientist at F5 Networks, which is based out of Seattle. I grew up here in Austin, moved out to Seattle, and just moved back recently. And I was like really heavily involved in the Seattle Python meetup. So it's a pleasure to, get introduced to the local Austin meetups, and I hope to, see all of y'all in the future. So again, as was mentioned, the topic that I am covering today is a library in Python called hyperopt, which does a thing called Bayesian sequential model-based optimization, SMBO. And why does this matter? What does this mean? First, we need to talk about hyperparameter optimization. For those who aren't familiar, most machine learning algorithms come with a set of knobs, to be tuned, that we call parameters. And usually the goal of tuning these settings is to minimize some sort of loss function. one of the challenges with hyperparameter optimization is that it's computationally expensive, because if you think about it, for every, especially when I get into explaining grid search, but for every combination of parameters that you set, you are estimating that many models, and so it can quickly get out of hand from a computational standpoint, when you're trying to find what are the right settings, for my particular model. Just a few examples of what we consider to be hyperparameters. In random forests we have, and these are not exhaustive, by the way, I just listed a couple from memory, but we have,
Erik, if I can ask something, some of the viewers here don't know about all of those algorithms. If you can tell a little bit more about those algorithms, I'll
Sure.
appreciate it.
Yeah, just from thank you. Great question. So if we zoom back and think of this in a very big picture sense, I am trying to predict some target. That the target can be continuous and be a regression problem. So maybe I'm trying to predict like the dollar revenue in a given quarter, or we often have a classification types of machine learning where we are trying to predict some sort of binary or discrete event. And when we are when we are modeling those things, we have some measure of error. And there are many different metrics that we use for error. I'm using that in a very broad term. But just to go through, so that's kind of the larger goal of a predictive model, a supervised learning algorithm. Although I will, as an aside, just say that unsupervised learning algorithms have loss functions too. So I do think this can actually apply out to that. But the point is this: we're trying to predict something. We have a set of algorithms that can do that. The algorithms that I listed are by no means exhaustive. I mostly, in my day-to-day modeling, work with binary classification. So just modeling an event, if it happened 1, if it didn't 0. And the output from that type of model is a probability of that event occurring. So to that end, random forest, if you're familiar with a decision tree, random forest is an extension of a decision tree where instead of building just one decision tree, multiple decision trees are built. And then basically the predictions from each of the decision trees are averaged together to produce the final prediction. So random forest is an ensemble model that kind of works that ways. And so some of these parameters, for example, is how many trees do I want to estimate? In each tree, what percentage of the columns of my features do I want to include into this, into a given tree? Similarly, sometimes they call this subsample, but for each tree, you may only want to pass in a certain percentage or raw number of rows. So that's just a couple of examples of hyperparams in a random forest. And XGBoost is another algorithm. It is also tree-based, but instead of being an ensemble, it's actually an iterative algorithm. So it estimates one tree, and I'm simplifying this to the point where I may be getting some things wrong. So if there are people who are more knowledgeable than me, feel free to jump in. But with XGBoost, you estimate one tree, then sequentially you look at the error, you model the residuals from that tree in a new tree, and then you create another tree and you model the residuals from that tree, and so forth and so on. So you can see some of the parameters in that are our learning rate, which is kind kind of the size of the step you take for gradient descent. And estimators is very similar to number of trees in random forest. Eta and lambda, I don't remember them off the top of my head. And then I'll just go through the last two, GLM, generalized linear model. This is where you are, for example, going to just do your linear regression or your logistic regression. But even for those kind of what we think of as classical statistical models, there are params on there like the L1 and L2 regularization terms, or the combination of L1 and L2, which is called elastic net. But that's GLM is just linear models and their extensions. And then finally, deep learning how do I explain deep learning? Maybe maybe I'll take the explanation of deep learning out, but I will say that like a single layer deep learning model with a sigmoid activation function, I believe, is identical to logistic regression. So they are, if you think of one layer like that, just many other layers, and we can kind of conceptualize deep learning. And some of the hyperparameters for deep learning are, again, learning rate pops up again. Some of these you'll see across algorithms, but for for deep learning, your activation function, so how you transform each output across the nodes is something you also might want to search with hyperopt, and then epochs also.
Erik, before you continue, there's a question in the chat, so I'll just voice it. What do the trees in the forest refer to? Because some people here do not have the concept. So give a simple example.
Sure. Okay. So yeah, I did mention those are, there's a lot of tree-based algorithms, but let's talk for a second about like the OG tree, which is just a decision tree. I think the acronym for the original is CHAID. I can't remember what that all stands for. But let's talk about how a single decision tree works. So again, random forest, XGBoost, they use multiple decision trees in different ways, but they use many decision trees. What a single decision tree does is it's basically a partitioning algorithm. And what it does is it takes your, I'm making hand motions, so you may want to look at my video. It takes your entire data set that you're training with, and it looks at all of the features, so all of the predictors that you are plugging into the model, or some subsample of the predictors that you're plugging into model. It searches around those, and it basically asks this question: if I take this single partition, which is the data set itself, what feature and what value of the feature do I split on such that the two partitions, or the however many partitions below the original entire data set, how do I split those such that I make each leaf of the tree pure? So that's like a lot of jargon, but let me try to explain it in a different way. So let's just say, I'm going to make an example from my experience. Let's say I'm modeling credit risk, and I have let's just say I have two variables, two inputs into my model. One is number of delinquent payments, and the other is time on file. So that time on file, how long you've had a credit history, that affects your credit risk. What a decision tree will do is search those two variables and then say, among these variables, where do I find a split? So where do I find a value to split on that produces two sub-partitions of this data that are more pure? So for example, maybe it searches around and it finds that, you know, the group that has 10 or more, you know, late payments on their credit report has a you know, maybe an 80% default rate, and the people who don't have a 20% default rate, then it's going to split on that value. And then now you have two different partitions of the data set. And then that process repeats again and again. So you're just building basically downwards and outwards depending on how many leaves you want to do. You're building splits that produce very pure, that are trying to produce pure, pure segments. And so if we tie that back to optimizing on a loss function, you know, you can have a tree, you can tell a tree which loss function to optimize on. So you can say, hey, find the split that produces, you know, the least amount of log loss, or find the split that produces the most amount of separation, which we call Gini. So that's kind of an explanation of what a decision tree does, but it's basically a recursive partitioning algorithm that produces pure and pure splits. When I say pure, I'm kind of talking about binary classification algorithms. So groups that have higher and higher percentages of event versus non-event. And as you grow that tree deeper, you get more and more accuracy. The problem with the old school trees is that they're very brittle. They overfit like crazy. The advantage to an original decision tree is they're extremely interpretable. They also lend themselves to, instead of having to pickle and store a model, you can just create a rules-based system. But like they leave a lot to be desired in terms of overfitting and being able to generalize to unseen data. I'll pause right there. Do you think that is a good enough overview of some of these supervised learning algorithms?
This is wonderful. I'm very happy that we're recording this. Thank you. Let's continue.
All right. So again, you know, to tie that all back, you've got a bunch of algorithms. And so for example, a binary classification problem, I can throw random forest, XGBoost, GLM, deep learning, LDA. I mean, the algorithms, you have many choices of algorithms, and then within each of those algorithms, you have many choices of settings, which just can overwhelm you in terms of compute and in terms of complexity. And so that's what hyperopt is trying to help with. And just again, like the whole point of hyperparameter optimization is kind of expressed in the top right corner here, which is to find the argument that minimizes some function, you know, some loss function, searching across that hyperparameter space, the large X there. So that's the goal of it. Whether it be sequential-based hyperparameter optimization or whether it be, you know, old school grid, this is the goal, which is to find this point of hyperparameter settings that makes your model more accurate. So there are actually many approaches to hyperparameter optimization. I link at the end of my presentation to some of the other ones. But traditionally, what we used and what I used for years was grid search, which is just searching the entire parameter space. So, you know, the advantage is that, hey, you have looked over the entire, you know, space of parameters. It's exhaustive, which can be thought of thought of as an advantage, but it's also a disadvantage. It's a brute force method that covers everything, and it doesn't remember what happened in the previous step, right? So it searches all those, and then it's up to you, end user, to look at the results from all of those different points and find, what validated best on your test data set. There's also random search, which is can be more efficient than a grid search, because you can feed it information about the distributions of some of the parameters, similar to hyperopt. But again, its problem is that it does not remember where, what it did. It derives no information from, if you look at all those little red dots, those dots are not deriving information from each other. And so in these two different graphs, right, or these visualizations here, the point in which the loss function is minimized the most by the hyperparameter settings is that like little white bubble there. So you can see grid will get there, and in this example, random search gets close, but really the main disadvantages from these is that they take a long time. Like, if there's any takeaway from this talk, is that the whole point of this is to speed up your hyperparameter searching. Any questions on the grid search and the random search approaches?
There was a question online about the X symbol. I think it's from the previous slide.
So there's a couple X symbols. X star is the combination of settings that satisfies that argument. And then the large X is the entire hyperparameter space. So it's just saying that look for the X star or the little x that is contained within the entire hyperparameter space. And then there's f of x, which is just the function, would be a loss function.
So if you look at your grid search, the big X is like all the possible location, and the small X is like the spot that you're looking for?
Exactly.
Thank you.
Exactly. Great question, by the way. So getting into hyperopt and sequential model-based hyperparameter optimization. Hyperopt uses a Bayesian approach to search your hyperparameter space. So in the top right, just very, very, very high level, is it's actually looking at the score of your loss. What is the probability of the score of your loss function given some set of hyperparameters, and what it needs. I'll talk about what it needs, and then I'll talk a little bit about how it works. What it needs is, again, a domain of a space of hyperparameters over which to search. So that big X that we just talked about, it needs that. It needs an objective function to minimize or maximize. So you can think about log loss for your binary classification. You can think about root mean square error for your regression. I mean, there's just you could even you can customize your loss function in here. So if you have a customized loss function, you can put that in here too. Then it needs a surrogate model of the objective function, some sort of selection function. A lot of this, honestly, these two are built in under the hood for hyperopt. And then it needs to be able to track it needs to be able to track the history of what has happened. And why that is because basically in each step, each hyperparameter combination that it considers, it uses that basically, it basically uses that theoretical framework in the top right of saying, okay, now given what I know from past runs of hyperparameters, where is kind of like the next where is the next combination of hyperparameters that is going to most likely reduce my loss? So if we go back to this slide here, we look at these two visualizations. We go back to this slide here. I had this animation. I don't have it anymore. But if we thought about animating like the time of these steps, this hyperopt would converge much more quickly. And you can see when it starts to converge, it really starts to bunch around that the minimum of the loss function there. And one critical advantage like for hyperopt is that it can search over discrete choices, right? So like numerical optimization for a function, if you're just trying to evaluate any function, period, like any simple function, numerical optimization is great. But for hyperparameters, you have a set of continuous hyperparameters, like learning rate is continuous, but then you have other things that are discrete. So for a support vector machine, which is just another algorithm that we could use for binary classification or regression or multi-class classification, you may want to choose kernel type to bring it back to random forest, which we talked about. The max depth, even though it appears on the face of it to be a continuous variable, it's actually discrete, discrete categorical values. So that's one advantage that hyperopt has, is that it's able to not only search among your continuous hyperparameters, but your categorical hyperparameters. Something that is like really worth some additional reading is it uses an algorithm for searching the hyperparameter space called TPE, which I believe is called a tree of Parson estimators. I am not going to get into that. It's extremely dense, but it's, at least to me, but it's worth a read. So I'll link that also in my sources. And at the end, what this does is sometimes it actually gets you better accuracy, especially like, for example, compared to the random search. The random search may not ever traverse that area where the loss function is minimized. So in that sense, you can get increased accuracy, but really, at least in my experience, the search over the spaces is quite a bit more efficient. So now I'm going to get like into the actual kind of Python section, and it's going to be pretty light of hyperopt. But hyperopt takes in a few arguments, and I'll show you applied examples of this. But for, hyperopt, really the basis of all hyperopt is this argument fmin. And with fmin, what it's going to do is it's going to take the information you pass and try to find the combination that minimizes whatever function you have passed in there. So again, for fmin, you need to pass a function, and it can literally be any function. I'll show you in a second, just straight up basic numerical functions, but we can extend this out to complex machine learning problems. You'll need to provide it with some sort of space to search. So for example, if you're setting your your max depth of your trees, you may want to tell it to range from 200 to 600 or something like that. but you need to tell fmin what hyperparameters you're interested in and what kind of ranges you want it to search through. And then you'll need a place to store the runs, and you'll also need to tell it which search algorithm to use. If you use anything other than TPE.suggest, you're just doing random search. So, you know, I would say you can do the other ones, but it kind of defeats the purpose of hyperopt. The other kind of main the other kind of main object in hyperopt is the trials object, and what that allows you to do is attach and store information from each of your hyperparameter runs. Again, I'll show you how that works, but you can see why you would, even if it comes back out and it tells you here's the best settings of hyperparameters, you may still want to kind of look through all the different runs and all the various goodness of fit metrics and whatever else you want to include in there. So trials is a way of basically making sure that information from each run is remembered and appended to a dictionary. So trials returns a dict. And then within the space that you want to search, you know, because this is a this is a Bayesian flavored, you actually can specify the expected distributions of the hyperparameters. In my experience, they are I generally just use uniform as my distribution, unless I have something like a choice, where then I have to use choice as my distribution. And then I think for learning rate, sometimes I'll use log normal. But that requires like a lot of domain knowledge and tuning and just kind of education about distributions. So in general, you'll probably be good with sticking with HP uniform for most of your hyperparams.
There was a question about the database that you actually would use. What do you use for databases when you run those?
Yeah, so for me, what I actually do is I'll take the dict. I work in Databricks a lot, and I'll take the dict that's returned and store it in a Databricks file store. But yeah, you can kind of choose where to write those. All right, I'm gonna. Oh, go ahead.
Thank you. Continue, please.
Sure thing.
Good.
All right. So we're gonna do a quick demo, just real quick. I'll show you a couple of examples. Apologize if you can't see this well. We worked a little bit to try and make it
this is
more
big
visible.
Enough. It's fine.
Okay, cool. All right, so I'll walk through just a couple examples. So here, I have I've just defined it like a very simple function, and the function is x squared minus y squared, and then I define a space here, and I say, okay, you know, here's the range for x, the range for y, and then here we see here's our fmin argument. So again, we passed in the function, we passed in the space. We're using the tree of partisan estimators. You can set there's a default for max evals. I set it to 10. you can kind of see, you know, how your loss function is performing over time and adjust that accordingly. But let me just run this real quick. So you see that's just a basic, that is just a basic function, right? And it's able to search around that space and find that, you know, this scalar value for x and the scalar value for y are the are the values that minimize the function given the range that we've given them. Then I'm going to move on really quickly to the storing the results with trials. So we have another function here. Sorry, I can't see my screen as well when I've exploded it. But sorry, 1 second, I apologize. Okay, so we have another really simple function that we're evaluating here. And we're just trying to find what value of x minimizes this x squared. The only difference between this and the last piece of code is now I've instantiated this trials object. And one thing I want to note about the trials object is that it can be parallelized in Spark using Spark trials, and it can also be parallelized in a MongoDB setting. So I have this, I run it, I get my best loss, that I defined, and I get my value of x that provides that. And then if now I actually have a history, if I look at trials, actually there's a couple different options with trials. There's several different results that you can get, but for this specifically, I just am looking at, you know, what's the result of the trials. So again, it's a dict that returns a ton of information about each run that is running. Or if I wanted to just see the results, I can see for each run, here is the loss in each run, and here's the setting basically. So those are like non-machine learning applications. Now I'm going to move into an actual two ML applications. So for you know, one actual algorithm that I didn't cover is k nearest neighbors. So let's say you would like to figure out what is my optimal k. In this piece of code, we define our space here as hey, we're telling it to look, you know, through 1 through 50 of
you might want to explain what is the iris example. Some of the people here are not from machine learning.
Sure, my apologies. Iris example, the iris data set is a classic and frankly overused machine learning data set that has some attributes about flowers, and the target for the thing that you are usually trying to predict with the iris data set is the species that the flower is in, given these features that you've been provided. So technically what this is a multi-class classification problem. So I've been talking a lot about binary classification problems, but this is actually, I think there are what, 3 or 4 different flowers that it could be.
Yeah, this sounds correct.
Yeah, all right. And so the point of this model is trying to find, you know, what characteristics are predictive of the species classification. And is a really, this setup is really simple. I'm only searching over one hyperparameter, which is just what is the number of nearest neighbors that you want to use. K nearest neighbors, I don't know if I want to get into explaining how KNN works. It's actually pretty simple, but let's just think of it as another supervised learning algorithm that works, again, for regression, binary classification, or multi-class classification. And again, the main setting is how many K do I want to put in there. So I have defined my space. I'm passing in my function, and again, I'm using the TPE suggest algorithm. And so if I run this, it takes a little bit longer because we're not just evaluating a basic function, we're actually using training data, and it returns that the optimal value of n neighbors is 4. And I can look at, again, I can look at the results and go through that. So I want to share one more example. This is an example that is applied. So this is actually from my work. I don't think I have anything super sensitive here, so I'll just give you an example of how we've used this to estimate and productionize binary classification algorithms. So I use a tool called Databricks that is in Azure. It's also in AWS, and it's basically like a collaborative notebook environment that also allows you to size up clusters and distribute using Spark if you want to go that direction. For this particular problem, what I am modeling is a purchase of a specific item in a given time frame. So what I'm trying to see is what features influence somebody's propensity to purchase within the next 3 months of this thing that we sell. So that is a binary classification problem, and the classification algorithm that I use for this model is XGBoost. So you can see here when I define this score function, I am kind of setting up my train and test set and telling it how to evaluate. I'm also specifying the type of model I want to use. I'm telling it to make predictions. And then this is really critical here. When you're modeling, you need to have some loss function in which to minimize. Now for me, I want to actually optimize on area under the curve. And so for those of y'all that are familiar with area under the curve, you actually want a really big area under the curve. And at this point right now, hyperopt only has an fmin argument, not an fmax argument. So I just have to do a little step here to invert the the score so that I'm actually minimizing the error, not maximizing the error. So I tell it, hey, I want to look at AUC as my metric, but then I technically define loss as 1 minus the AUC, and then hyperopt will optimize on that. Again, you can use loss functions that are prepackaged. You can also program your own customized loss function. So we can see it gets a little bit more hairy when you're really trying to search through a space. I'm not going to go through every single setting here, but I'm looking across the number of trees, depth, subsample, column sample learning rate, alpha, lambda. I don't even remember what some of these are sometimes. And then one other thing I want to note is that if you really want to accelerate your training, hyperopt plus a GPU enabled machine is going to really speed it up. So this kind of I think the data set that we use for this is 8 million rows by 300 or 400 columns. And that can definitely take even on a pretty beefy machine that's not GPU enabled, that's not using hyperopt, it can take a few hours to train, you know, that many models. But we're getting the advantage here of using a GPU, and also we're getting that informed search from hyperopt. And so I tell it, you know, to return the best model. And then I'll just show you in the very next cell, I run, let me just pause and ask, can everybody see everything in this cell? Because for me on my monitor, I can only see part of it.
We can see up until line 14. The cell is pretty big. Okay,
cool. Okay. Yeah, so this is it in action. There's a couple other things going on here. We've been experimenting with this thing called ML Flow, which if you combine with hyperopt, you can get a lot more robust tracking and a lot prettier output. And you can also log models and serve models with ML Flow, but that is not really the point of this talk. And I just want to show just kind of how this operated in the real world. You know, I actually told it to run multiple trials just to see in case, you know, to see if we were missing anything. And you can see after a couple of trials, we get after the 6th trial, there's like a slight reduction in loss, but like at this point, really the first run was able to accomplish everything. So if I was going to go back through and redo this, I would actually just only have one run, and that took like an hour, and also it returns this pretty little dict here that tells me for my model, here are the best hyperparameters. I think there's a way to harvest that actual best model out from either XGBoost or hyperopt, but I'll just show what I ended up doing, which is kind of crude. And I just took that dict right there, recorded all the values of the dict, re-estimated the model with my optimal hyperparameter settings, and then I just I dump my model and save it, and it's ready to go. So I guess my point in showing that is that we did in fact see quite a bit of speed up in terms of how long it took for us to arrive at the optimal set of hyperparameters. Like I said before, when we were doing grid, it could take hours and hours and hours. This took an hour for a fairly large high-dimensional data set with a lot of different hyperparameters in there. So it's just a ton of different options to evaluate, and it really quickly came to the optimal setting. So you know, in conclusion, you know, hyperopt allows for more efficient searching of the hyperparameter space. So it can really reduce your training time, and sometimes it can give you better accuracy. But I did want to, as I mentioned earlier, there are many different hyperparameter optimization, sequential hyperparameter optimization methods. and I actually, right before we started this talk, I was reading an article that builds off of that combines the tree of Parson estimators with hyperband, and it's called BOHB. So there's just like there's a lot of different. This isn't the end all be all of hyperparameter optimization, but like I said before, we did use it in my current position, and we were satisfied with the results. It's open source, and I think it's a great resource. So with that, I'll end and field any questions if there are any. Thank you.
First, I would ask everyone to unmute themselves and thank you properly by clapping, whoever is left here.
Thank you.
Yeah, okay.
Yeah, good job.
Okay, hopefully we won't have too much feedback. I have questions, and you had many questions throughout, but I have one question at the end. This is a nice optimization technique. Can it be useful for cases where you don't want to actually do hyperparameters, you actually want to do parameters? Do you think it's useful?
So instead of hyperparameters, I guess what, like, in terms of parameters, are you like, are you referring to I guess can you give me some context about what you mean by for parameters, like the coefficients of the model, or
yeah. So you said that this technique is useful when you actually have things like a mix of like continuous and non-continuous parameters.
Yeah,
Think about some functions, or some models actually have combinations of those.
absolutely.
So do you think it might work, or did you ever use it for something like this? Or
I haven't used it for something like that, but I think, you know, my main kind of message is that, especially with those evaluations of those very simple functions, is that it's extremely flexible, right? It doesn't have to be for machine learning. It doesn't have to be just for simple functions. You know, anytime that you need to search a space, and that you have some metric that you need to search a space, and you're trying to find a minimum. I think it could be useful in maybe any of those situations.
and how many examples do you need? Like 1 or 2 or 3, or do you need like hundreds? Or
Like how many records do you need?
so if I have a function, no, forget the records. If I have a function, how many evaluations of the functions do I need for this to become useful? And I'm not exact number, but like hundreds, tens, thousands, 10,000s, or singles.
Yeah, that's a great question. I think, you know, I think in the if we zoom in here, I think the default max evals you can see right there is gigantic. But
Okay.
in my experience, so I would actually I would start small and build, because in my experience, at least for like that last model, it solved very quickly. It didn't need that many. It didn't need that many evaluation steps to figure out that it had gotten to where it needed to be. And just like with grid or anything else, you can actually program in an early stopping threshold and say, hey, if the next iteration of hyperparameters doesn't improve the loss by this much, go ahead and stop the search. So if you toy around with that, you can kind of get an idea of what is the best number of runs for your particular domain.
Yeah. Might be useful for some other things. I can think of some.
Yeah, I think it's really cool. I really like hyperopt, and I'm looking forward also to researching all the other hyperparameter tuning. So maybe I'll come back in a year and talk about something else.
Oh, you'll be very welcome. If anyone has any question, please jump in.
Yeah, and also I just would say, if please feel free to reach out to me on LinkedIn. I love talking about machine learning, Python, that type of stuff. So I'm happy to chat offline about really anything about this stuff, because I just think it's a great career and really fun.
I agree. Well, it seems no one is asking any more questions. Either people are shy or it's for the utmost experts. Because I must say, you've shown quite a bit of knowledge now. So I think everyone is overwhelmed. So I'm going to thank you again, and please thank Erik as well.
Thanks a lot. I really appreciate it, y'all.
And I'll stop the recording now, but anyone is interested, we can continue hanging around here. So I'm stopping the recording. Please stick around.